well, less, 1 minute, because we are going to take the official photo.
Oh, of course, yeah, good.
Yeah,
Good, yeah.
excellent. So
Sure, let's do that.
I want to.
Yeah.
This is quick.
So,
Sorry? So we are going to take it just in 1 minute, because we are going to take the official photo. So if you want, can you came here, please?
Eso, la traigo. Sí. Vamos a tomar café.
¿Acá?
Sí. Sí.
okay.
Fíjense, ahí unos arriba en el segundo escalón, en el primero ya. Abajo, como equipo de fútbol.
Sí.
Then in the center.
Yeah.
Okay.
Okay.
Aspetta.
Gracias.
Okay, good.
Okay, so let's continue, please.
Okay, everybody, welcome back to the final part of my two lectures. So, I want, in this final part, about more or less half an hour, to describe what is coming next. So, in April of this year, the LIGO detectors began operating again, also the Virgo detector, on April 1st, 2019. So, we call this our third observing run, O3, and it's very different, because during O3, we announce the candidate events more or less immediately. They are available on various websites. They are automatically alerted on Twitter. And this is to give astronomers the maximum possible opportunity to look for electromagnetic counterparts. So I showed this slide yesterday. In the first 6 months of operation, we saw 33 candidates. That was until September 30th of 2019, and then we took a break to carry out more commissioning and more improvement to the detectors. So the second part of O3 will begin on November 1st, and I need to chair a telecon about the start of O3 that begins at 11 o'clock. So I must finish on time. Maybe this is good for you also. So I do apologise, I will not be able to join you for coffee, but I hope the telecon will end quite soon to let me come back and to listen to Paolo's lecture. And of course I'll be around in the afternoon and during lunch. I look forward to discussing more. So we are preparing for the second part of O3. What has happened in the first part? Well, you can find information on this website here. This is the Gravitational Wave Alert Candidate Database, GraceDB, and we have various websites that present the information Some of it really just designed for astronomers, and some of it designed for the general public, so it looks a little more friendly. So the one for the general public is probably this website. It's called Chirp. It's run by our colleagues in Birmingham in the UK, and they have just completed making an Android and iPhone app that will be ready by Friday as well, so you can download them for free from the App Store or from Google Play. And what this will do is it will send an alert to your phone when there is a candidate. So don't blame me if it wakes you up in the middle of the night, because there are right now a lot of candidates. So on the web page for the app, and again this will soon be available for mobile devices, there's a sky map. Now this doesn't look very interesting, but you see the reason it looks quite bland is because the sky localization for this event was very good. It was only about 30 square degrees, as good as the neutron star binary from 17th August 2017. But this one is more distant. And this one, our best guess is that it is actually a neutron star black hole binary. Now we haven't seen one of those before, so this would already be something new and quite exciting. So there is zooming in and showing also some constellations. You probably can't read the detail, but it's on the boundary between the constellation Cetus and the constellation Sculptor. So that's the posterior probability of the sky location, and it's, as I said, about 30 or so square degrees. There's already been a lot of publicity about it. This is one of the things we're discussing in our telecon in half an hour. How do we cope with this change of the way things work? Because we put out the candidate for a good reason so that astronomers can go look for an electromagnetic counterpart. But this also means that blog articles and magazines, they run stories about it. So there were stories in August about this just a few days after the candidate. In National Geographic, there was even a story in The Economist. So it is only a candidate, and it's quite challenging for us to get used to this, that the world is already talking about our candidates before we've even confirmed if they are real. Now, let me give you a small secret. We do think this one is real, but we are not yet sure if it really is a neutron star black hole binary. The neutron star black hole binary is our label. It's from our estimated masses of the two components. And we don't want to release all of that information, otherwise, frankly, people could go write papers about these events before we have time to do it. It's a challenge that all astronomers face when you have very valuable observational data. How do you get enough time to write the papers yourself before everyone else can? So our classification scheme is quite crude. What we say is, if the mass of one of the candidates is above 5 solar masses, and the other one is between 1 and 3, then we call it a neutron star black hole binary. That's just based on the most likely scenario with those masses is that we have a neutron star and a black hole. If both of them are above 5 solar masses, then we label it a binary black hole system. We've seen lots of those. If both are between 1 and 3, then we say it's a binary neutron star. If the masses are below 1 solar mass, we've probably made a mistake, but if we did see such an event, of course that would be very interesting as well. We haven't yet. And then there's this called the mass gap, where the events are between 3 and 5 solar masses. Again, it's just a label. We don't know if there truly is a mass gap. It's just that we haven't so far seen neutron stars more massive than 3 and black holes less massive than 5. They probably exist. Maybe they exist, we don't know. But it's a useful way to categorize the type of event. Frankly, this is to let us provide some information to our electromagnetic astronomer colleagues. For example, Steve Smart, who's a very eminent EM astronomer works a lot on supernovae and other transient events. He's at Queen's University Belfast. I see him a lot at various meetings, and he says, kind of joking, but partly true, that he doesn't bother getting out of bed now for the binary black hole candidates. So if we are telling our astronomy friends that this one is probably a binary black hole, that will allow them to make appropriate judgments on how to manage telescope time. If we tell them it's probably a binary neutron star, and even better if it can be well localized, then of course they're going to be more excited about that to allocate more telescope resources. So since August, we've been carrying out analysis on the gravitational wave data to try to work out if it really is a neutron star black hole merger. Finding a nailed-on EM counterpart would certainly help, but again, we must be cautious. There's no guarantee that there will be an EM counterpart, either intrinsically or maybe one that we would see. In other words, there could be a counterpart, but it's too faint. Or there might just not be one, because if the difference in mass between the neutron star and the black hole is sufficiently large, then the neutron star will be swallowed too quickly to release a strong EM signal. So we haven't seen a nailed-on EM counterpart for any of those 33 candidates. But don't panic. That doesn't necessarily mean something is going wrong. It just means that we got very lucky in August 2017. Because even the BNS candidates that we've seen are much more distant than 170817 was. We've mainly seen binary black holes, which probably don't have an EM counterpart anyway, and the neutron star black hole candidates, we're not sure. But it's a very interesting problem that our EM colleagues have, how to efficiently manage their telescope time so they don't miss anything, but they accept the fact that a lot of the time they're going to be looking and there's nothing there. Obviously, having good sky localization helps. If you're looking in this region for a possible signal with an optical telescope, it's a lot better than looking in this region. So this was the event from 14th August, where it was observed by Virgo as well as Hanford and Livingston. So having networks of detectors is really going to help a lot in the future. Let me just mention another interesting one. August 28th, there were 2 gravitational wave events that arrived within about 20 minutes of each other. Again, they were announced automatically on Twitter, and then one of my jobs is to manage a team of people to put out additional information on social media very soon afterwards. But we also monitor what other people are saying on social media so that we can respond to questions but also get a feel for what people are thinking. And sometimes our social media posts we try to just make a bit humorous. So I'd said here, waiting for gravitational wave sources is like waiting for a bus. You wait for one and then another one comes along just after. And that was partly just to deflect too much kind of serious thinking about 21 minutes apart. In fact, you can do a simple exercise. At the rate that we are getting events now, you can ask the question, for a Poisson rate, how likely would it be that you have 2 events only 21 minutes apart? And it's not that unlikely. But what's interesting is that they also were quite close together in the sky, even though they weren't very well localized. So before we knew it, people were saying on the internet, maybe you can't read this from the back, let me read out. This is freaky. Perhaps the simplest explanation, barring an instrumental or data handling issue, is that this is the first gravitationally lensed gravitational wave detection. So take it from me, it is not. Because the sky localization is not perfect, but it's good enough to completely rule out that these are in the same sky position. They're in similar sky positions, but not overlapping. And the gravitational wave deflection would be very small, just like it is for light. But it's great that people are so interested. And at the very end, if I have time, I will say a few words about the lensing of gravitational wave sources, because it is coming. We will see it eventually, just not yet. Okay, so our commissioning date began on October 1st. As I said, it will end on October 31st. So I've got to go do this telecon in 24 minutes. So let me not hang around too much. We had all these public alerts. What I want to say is a bit more about what comes next. So the second part of III will take us through until spring 2020. And during that time, CAGRA will begin operation. And then in the mid-2020s, LIGO India will join the network. So the CAGRA Memorandum of Agreement ceremony took place in Japan 3 weeks ago now. And again, there was a bit of press coverage of that, but as I said yesterday, don't get too excited because CAGRA will take some time to achieve sufficient sensitivity to really contribute very much to the network. But we will eventually. It will just take some time. So if you want to find out more about the details of that, there's a document. Oh darn, I forgot to put the web link in. So I'll update this for the PDF and include the archive reference. But this is a paper that just was updated in the archive very recently. It's from a Living Reviews in Relativity article, which describes different observing scenarios and the prospects for detections in the future. So 03 is what we're in right now. 04, we run 22, 23, and then 05, that will really take us into Advanced LIGO Plus, upgrading the Advanced LIGO detectors even more. That will take us through to the middle of the next decade. So these are target distances for binary neutron star mergers. We would be able to see binary black hole mergers much further away. We already are seeing binary black hole mergers much further away. But the real key here is to look at the difference between 01 and 05. So it's a factor of maybe 4 or 5 in distance, which corresponds to a factor of more than 100 in volume. So of course we expect the rates to increase a lot. So this diagram, let me save a bit of time by not going into the details, but we're potentially looking at rates that could be several hundred times what they currently are, and also that will overlap with better electromagnetic surveys, like the beginning of the Large Synoptic Survey Telescope, so that's exciting too. And because we have more detectors, we can localize on the sky much better. I think I showed this before. So this is Hanford, India, CAGRA, Livingston and Virgo. And look, the sky localizations are typically much, much smaller than they are here. So we can expect to get many sources localized to about 10 square degrees on the sky. Now throughout all of this, the science goals that we are interested in using gravitational waves for are expanding because, well, I talked before about measuring the Hubble constant, but maybe we want to do other things as well. These are just a long list of questions. Essentially, we want to move away from just detecting gravitational waves to just using them the way that we use other types of astronomical data, radiation. So that's a long list. I've talked a bit about the Hubble constant measurement. Let me now try to say a bit more about the prospects for using gravitational waves to measure the accelerating expansion of the universe. So, for the immediate future, through to the mid-2020s, really the best we can expect to do is to measure the Hubble constant. We saw that already we've done that, but not very well, so we can't resolve the Hubble tension because the uncertainty is too large. But could we expect to do that in the future? By the time we have LIGO India and the detector in Japan, CAGRA, operating at design sensitivity, what these curves are representing is different types of events and the typical error on the Hubble constant. So we can aspire to get down to errors of about 1%, which is obviously where we'd like to be. But crucially, it will require finding the electromagnetic counterpart to get the redshift. Or doing it with black holes, this dark-siding method, but doing it with so many black holes that eventually you also get a decent estimate of the Hubble constant. So both have challenges. With the dark sidings, the challenge is much more about having a reference catalogue with reliable redshifts to really quite significant distance. With the binary neutron stars and maybe neutron star black holes, the challenge is to see the electromagnetic counterpart and to find it in a sky area that might be 10, 20, 30 square degrees. LSST, as I said, is going to help a lot because it has a very large field of view. It's got a 3 gigapixel camera, 1 gigabyte image every 20 seconds, 30 terabytes every night. So everyone's going to need larger hard drives. And we expect that that might have as much as millions of transient events every night. So in addition to just collecting the data, the problem is going to be identifying the false alarm rate, events which are not instrumental glitches, but they are astronomical transients which are not kilonovae. They're not the counterpart of a gravitational wave source. So all of these are really interesting problems, I think, for us to work on in the years to come. But what about beyond? So moving into the 2030s, the game there will be to go beyond roughly redshift 1 to observe gravitational wave sources all the way back to when they began to form. So for ground-based detectors, this means third generation gravitational wave detectors. And there are 2 big projects leading the way. In Europe, a design study called the Einstein telescope. The goal is to get 100 times better sensitivity than initial LIGO. So we've already got about 10 times more sensitivity planned for advanced LIGO through to the mid-2020s. How do we get 10 times better? It's challenging. One of the biggest challenges is the seismic noise at low frequencies. So the Einstein telescope proposes to solve that by building the detector underground and using cryogenic cooling to minimize the thermal noise in mid-frequency ranges, whereas the other project led by the US called Cosmic Explorer is proposing one on the surface with broadly similar technology to advanced LIGO, but just very long, 40-kilometer arms instead of 4. So which of these designs will work, will succeed? We don't really know, but there's a worldwide collaboration leading the study of these. So I've been involved a bit in that with graduate students who've been looking at the sky localization capabilities of a network of third generation detectors. I don't want just one of these to be built, I want them all to be built. So there's interesting questions about where you should locate them and how sensitive they need to be to address particular challenges in astrophysics and cosmology. That's pretty much what I said in the previous slide. A triangle for ET, underground, and able to have both low and high sensitivity of frequencies. And then Cosmic Explorer is a single 40-kilometer detector at LIGO Hanford and a single 40-kilometer detector at LIGO Livingston. So there's a broad range of science goals for these detectors too. Again, you probably can't read the detail, but everything from fundamental physics and extreme gravity to cosmology and cosmography. And what makes all of this feasible is that the sensitivity means that you get high signal-to-noise ratio events even at redshift, well, 10, 15. Frankly, we've no idea if there are sources at such redshift, but if there are, these third generation detectors will see them. So you are volume limited, not like flux limited or stream limited. So, current state of the universe, we heard a lot about this yesterday from Paolo and from many of the other speakers. I frankly don't really know what's going on with dark matter and dark energy, so let me not try and pretend that I have the magic answer. All I'm really saying is that it would be good to have different methods to investigate these questions, and gravitational wave science could provide that. Of course, we'd all like to answer this question and even to know if it's a meaningful question. And so far, probably the most popular game in town, notwithstanding all the problems that we've discussed yesterday, is lambda CDM. Okay, we mainly talked about the problems with the CDM part, but there's plenty of problems with the lambda part too. So one thing that might help us address that is to understand if the dark energy is evolving. And again, we all have our favorite parameterizations for that, as well as lots of other models that people here work on. If we just restrict ourselves to the standard parameterization, some of the recent work on this by my students, by other groups, have been considering how well we could constrain W0 and WA from networks of third generation detectors. So, of course this is way down the line, it's in the 2030s, it's very ambitious. But the thing to emphasize is that it would be competitive with EM cosmological probes on a similar time scale. There's no good us saying, here we'll do gravitational wave cosmology if it's not able to compete with what we could do with the CMBR, with supernovae, with baryon acoustic oscillations. It's not better than those methods, but it's comparable, and it's a different set of systematic errors that you're subject to. So it's got to be worthwhile to try. And then just finally, we've got other parts of the gravitational wave spectrum as well. So everything I've really talked about so far is down here. And I'm not going to have any time to talk about this, but let me just say a few words about space-borne detectors in the next 5 minutes to finish. So LISA is the most well-known. This is now officially adopted as a selected mission by the European Space Agency. And it will also observe sources to very significant redshift. Massive black, well, really supermassive black hole binary mergers to Z greater than 20. Again, we have no idea really if they exist at such redshifts, but if they do, then LISA will see them. What was it they said? If you build it, they will come, as they say in Field of Dreams. So this is going significantly beyond what we can do with supernovae or baryon acoustic oscillations to probe the Hubble diagram to quite significant redshifts. Now there are problems to be overcome. For example, this is from an old paper now, but it highlights the effects quite clearly. This is at redshift 1, and it's a sort of supermassive black hole binary. So exquisitely accurate, but there's a long tail due to parameter degeneracies. So again, it might require some form of multi-messenger astronomy approach to help us break those. But what would even be the EM counterpart of a supermassive black hole binary? Maybe we'd have to rely on information about the host galaxy. I don't know. There's a lot to explore there. But there are also other types of source that LISA would observe apart from compact binary coalescences. There are sources called extreme mass ratio inspirals that could allow us to perform even more precise tests of GR to explore the structure of the gravitational field to very high order multipolar expansions. And the waveforms are very complicated, so this presents a lot of data analysis challenges as well. That's the part I know more about. I rely on the theorists to solve all the other stuff, and then what I've got to do is work out how to extract the parameters in a sensible time using data analysis methods that maybe we haven't even invented yet. We've got about 15 years to get on top of all of this before LISA flies. So finally, let me just mention something about lensing. So I wish there was more time to talk about this. I'll maybe try and come another time and spend longer, because I know there are people here with very close interest to this. Indeed, that's really how I got the opportunity to work with Antonio Herrera Martin, who had been a maestria student here with Luis Orena, and then he came to us in Glasgow, and his PhD thesis was on electromagnetic strong lensing observations, but he also did some very nice work on wave dark matter with gravitational wave lensing. So what I mean is a gravitational wave source which is lensed by a dark matter profile that's described by the wave dark matter that we heard Tonichu and others talk about yesterday. So the bottom line is, look at this one. Again, it's a bit blurry, you can't see the details, but what we're interested in, it's not that I necessarily am a passionate advocate for this model. Others in the room are better qualified to argue for the model or not. But what I'm interested in is this plot, the fact that the parameters of that model show up as different gravitational waveforms. So we have some prospect of inferring the parameters from analysis of the gravitational wave signal. So we need to get one of them lensed first. But if we saw a lensed waveform, the idea is to constrain the properties of the matter profile that caused the lensing. And I think this could be a very interesting methodology in the future. So there's a bunch of papers starting to come out of the collaboration on this. So I was arguing for gravitational wave lensing as an interesting phenomenon about a decade ago, and nobody believed me. Well, not that they didn't believe me, but they said, yeah, worry about detecting something first. They were probably correct. But now it's starting to gain some momentum. So I do think this could be very interesting to work on. And then another interesting topic, again, I'm not here as a strong advocate for primordial black holes. Others are. And I'm fascinated to hear them talk about them. But my interest is in how could we use gravitational wave data to say something about PBHs. And the key here is the spin distribution, because PBHs would be formed separately and then dynamically captured before they merge. So if LIGO is seeing PBH mergers, then they are dynamically captured PBH mergers, as opposed to stellar mass black holes, some of which were maybe already in a binary system before they became black holes. So that will mean their spin distribution would be different. And there's some really interesting Bayesian inference problems there, trying to extract that information from a population. So there's a couple of things that people might want to talk to me about while I'm still here, or keep in touch afterwards. As I said yesterday, I stopped being department chair in about 8 months, and I'm really looking forward to a year when I can just devote time to research. Maybe I'll come back to Mexico and visit and find out more about what people are doing, but it's been really fascinating hearing some of the research going on, and I can see lots of ways in which it connects with some of the growing activities in gravitational wave cosmology. So there we are, there's some of the things I've talked about, some of them very briefly, some in more detail. But the main thing to stress is there are lots of coming attractions. So I showed this slide yesterday just to emphasize again the web page. There's a lot of cool stuff you can check out. There's our science summaries that I mentioned as well. And there's one of the more recent ones on the data analysis methods. And then there's the Gravitational Wave Open Science Centre. I had meant to leave a bit more time so I could connect to the internet. I'm so sorry. But again, because of this telecon, I should stop soon. But please do come and chat to me. I can show you on my laptop later some of these codes and point you towards how you can play with them yourself. You can even follow us on YouTube and, of course, on social media. So let me end with this one. We came up with this at the time of the neutron star merger. We call it the in-spiral toast. So I look forward to having some of those tonight, maybe, at the dinner, and I hope I've convinced you that gravitational waves have a very bright future. Thank you.
So we have a couple of minutes for questions.
Yeah.
What about this other phase that you know? I mean, the quantum nature of these things?
Sure.
Do you have proposals or something to measure this duality that some people suggest now?
Well, sure. So a good analogy here is the ultraviolet catastrophe. You know, radio waves, by and large, you can just treat classically. It was only at those shorter wavelengths, higher frequencies, where all the quantum effects messed everything up in the early 20th century, and then Planck and Heisenberg and all the others come along. So, in a sense, we are probing gravitational waves on much longer wavelengths where the classical regime is still perfectly fine. The only small counter to that is the example I showed, the phenomenological model for gravitons being massive and how that would affect the waveform. But there are some other interesting possibilities. Now again, I am not an expert on this, but some people have written some papers claiming evidence of quantum echoes in the data analysis. So I've chatted to some people that know much more about this, people like Bernard Carr, Andrew Liddell, Garcia Belludo, and so on, and they've all said, well, that the idea is fine, it's just, our judgment is that the data analysis that people have done, because they are outside the collaboration, has missed some important details. So we don't actually think there is any evidence of these quantum echoes yet. But the effect all that had, that those papers had, was for us to set up a small group within the LIGO collaboration, where we are now looking for those effects when we get a candidate. But there's only so many hours in the day. We need more people to help with those kind of non-standard analyses. So the short answer is, I don't think there's any evidence yet, but if you're interested in getting involved in any of that, please do talk to me, because I think that's what we want to be looking for. We want to be pushing GR to the limits. I was in charge of the Twitter campaign when we had the first detection announcement, and Obama tweeted, #Einstein was right. We were pleased that he took an interest. The current guy doesn't seem to care, but that's fine with us. But Obama saying that, it wasn't really the correct thing to say. What he should have said was, Einstein isn't wrong yet, because we're much more in the business of testing it. So watch this space. Thank you. Yep, absolutely. Again, the data, there are two practical possibilities. One, join the collaboration and get involved in doing it within, or just wait a few months, the data will be released, and then you can do the analysis yourself. So either way, somebody should do it. Paolo?
I've been very fascinated by the amount of energy, which is released in making the space-time flat again.
Yeah.
But this energy can be really transferred to other parts of the universe or not?
Well, in some sense it was there before, locked up in space-time, and then space-time has just reorganized itself, and you've got these waves. In a way, I suppose part of what your question is starting to think about is there any way we could harness that energy? I get asked that a lot in public lectures, and I say, well, probably not. Who knows? I make the contrast with electromagnetic radiation. Maxwell predicted the waves, and within 20 years or 30 years, Helmholtz and Marconi ultimately was able to generate them. We have no idea how we could do that with gravitational waves, or even to capture that gravitational wave energy. You could have hoverboards and anti-gravity and all of that if that were possible. So in a way, that again underlines just what a remarkable piece of technology LIGO is, because it's not like absorbing the gravitational wave energy, it's just like a test mass responding to the fluctuations as they wash past. So, that wave energy has just kept on going, spreading out through the universe.
You mentioned repeatedly that we don't expect an electromagnetic signal from a black hole collision. So I guess this is because somehow you are thinking that the accretion disk is negligible. Can we put bounds on the size of accretion?
Again, I'm not an expert in this, so forgive me if I oversimplify or even get something wrong, but I have been talking to some people about that, because this will be crucial for LISA. LISA will not see neutron star binaries, so really, if we want an EM counterpart of LISA sources, it's going to have to be from the accretion disk around the emerging black holes. So the issues are really twofold. One is, does the inner part of the accretion disk get cleared of material so that there's nothing there to emit, to shine? And secondly, even if that doesn't happen, is the electromagnetic radiation happening at such a different time from the gravitational wave radiation that you can't easily connect the two. The timescales for LISA are much longer, so if you get an EM signal 1 year before the gravitational wave signal, what use is that? You know, it's very, very hard to do the matching. The ground-based is different because the black hole mergers, if there was an EM signal, presumably the EM signal would be close in time. So we can certainly look. I said that my colleague doesn't get out of bed for the binary black hole mergers, but plenty of astronomers still do. And I think it's important that we keep looking. There might be some signal from an accretion disk around the source. Yeah. Okay.
Very well, so thanks again, Martin, for this magnificent lecture.
Thank you.